Hi, I hope you are having a good day. We are the team number five, and we are talking about six topics that are relativity, invariance of physical laws, relativity of simultaneity, relativity of time intervals, the Lorentz transformations, the Doppler effect for electromagnetic waves. And our teammates are Torres, Rico, José Armando, Téllez, García, Fátima, Rivera, Grimaldo, Emmanuel, Palomares Mar Christian, Galván, Pacheco, Abisaí, and Lara, Rendón, Audrey, Ernesto. And we are going to start.
Relativity in physics refers to the theory of relativity developed by Albert Einstein in the early 20th century. The theory of relativity is actually two separate theories: special relativity and general relativity. Special relativity is based on the idea that the laws of physics are the same for all observers, regardless of their relative motion. This means that the speed of light is constant and independent of the observer's motion. Special relativity also introduced the concept of time dilatation, which means that time appears to pass more slowly for objects that are moving relative to an observer. General relativity is a theory of gravity that describes how massive objects distort the fabric of space-time. According to the general relativity, gravity is not a force between objects, but rather a curvature of the space-time caused by the presence of massive objects, and this theory has been able to explain many phenomena, including the bending of light around massive objects and the existence of black holes. Both special relativity and general relativity have been extensively tested and have been found to be extremely accurate in their predictions, making them essential components of modern physics.
When Einstein first hit upon special relativity, he thought one effect of special importance, so much so that it fills the first second section of on electrodynamics of moving bodies. It is the relativity of simultaneity. According to it, internal observers in relative motion disagree on the timing of events at different places. If one observer thinks that two events are simultaneous, another might not. At first, this will seem like just another of the many novel effects relativity brings. However, as we explore more deeply, you will see that this is the central adjustment Einstein made to our understanding of space and time in special relativity. Once you grasp it, everything else makes sense, and you will do, and nothing quit makes sense. Um, and the concept, the relativity of simultaneity, is the concept that distinct simultaneity, one another to separate, specially separated.
My name is Angel, and I'm going to explain how the invariance of physical laws is a characteristic important in the physics. So, to begin, I want to explain that when you in the physics, when you are making an experiment, you can recreate all these experiments and you are going to obtain the same result in all of your different experiments if you are in the same frame of reference. So that's mean that if you make an experiment here in Mexico and then you repeat it in Korea, you must obtain the same evidence and results that you obtain in both of them. For example, when you are practicing making exercise above the parabolic throat, you calculate the trajectory of a ball, for example, that was thrown in a kind of ellipse, and you can make two ways. You can use two ways to resolve this problem. One is that you are considering that the ball was thrown with a value of velocity that you know, and you know maybe the time or the distance in all of this process. And this is the first, when you consider that the first step is when the ball was thrown. But also you can use an opposite way in which you are considering only the moment in which the ball is coming fall, and you are going to obtain the same time, the same velocity, the same, well, the same gravity, because you are in the same planet. And all of these dates, is despite you are considering a different frame of reference, and you have the same energy, the same work, the same power, static and kinetic, in all of these different way to resolve the same problem. So this is a characteristic of the invariance of physical laws, and demonstrate the importance of the developing physics theories in any particular reference frame.
Hi, well, my part is relativity in time intervals. Well, what is time intervals? Time intervals is refers to how the time is affected by the perception of different observers. Like, the observers are in different states of motion. The time interval between two events can measure it in any frame of reference, but the result may vary depending on the observer's motion. For example, the speed of the light, well, the speed of the light is a constant, because that doesn't depend of the observer state, because the speed of the light has a constant speed. So this means that the time it takes for light to travel between two events is also constant. For example, if two events occur in different time and in different places, the light takes time to travel to one to another. The time interval between the events and the time interval between that is affected by the distance and by the places. For example, if an observer moves at the speed close to the speed light, the perception of the time of
The relativity of time intervals is a fundamental concept in modern physics that arises from the theory of relativity developed by Albert Einstein. It refers to the fact that the perception of time intervals is relative to the observer's motion and the gravitational field they are in. In special relativity, the relativity of time intervals is a consequence of the theory's postulate that the speed of light is constant for all observers, regardless of their motion. This postulate leads to the phenomenon of time dilation, where time appears to pass slower for objects that are moving relative to the observer. The faster the object moves, the more pronounced the effect becomes. As the object's velocity approaches the speed of light, time appears to slow down significantly. In general relativity, which includes the effects of gravity, the curvature of spacetimes also affects the perception of the time intervals. According to the theory, the presence of mass or energy curves spacetime causing it to distort around the object. This distortion affects the flow of the time in the vicinity of the object, leading to the gravitational time dilation. In other words, clocks in stronger gravitational fields appear to run slower than those in weaker fields. The relativity of time intervals has been confirmed by numerous experiments and observations. For example, the famous Havel-Keating experiment involved flying atomic clocks around the Earth in opposite direction on commercial airlines. The experiment demonstrated that the moving clocks experienced a slight time dilation compared to the stationary clocks on the ground, confirming the predictions of special relativity. Similarly, the gravity proof B experiment measured the effects of gravitational time dilation around the Earth, confirming the predictions of general gravity relativity. The relativity of time intervals has significant implications for our understanding.
The Doppler effect is a phenomenon that occurs when there is a relative motion between source of waves and an observer. This effect applies to all types of waves, including electromagnetic waves such as light and radio waves. When an electromagnetic wave is moving towards an observer, the observer detects a higher frequency of waves than if the source was stationary. This is because the motion of the source compresses the waves, making them closer together and thus increasing the frequency. This is known as a blue shift. Conversely, when an electromagnetic wave source is moving away from an observer, the observer detects a lower frequency of waves than if the source was stationary. This is because the motion of the source stretches the waves, making them farther apart and thus decreasing the frequency. This is known as a red shift. The Doppler effect for electromagnetic waves has important applications in fields such as astronomy, where it is used to measure the speed and direction of celestial objects based on the observed shift in their spectral lines.